Okay. So, শুভ সন্ধ্যা সবাইকে. Very good evening, everyone. Uh, my name is Samrit, and I am honored to be your host today. Welcome to today's podcast session, Cosmic Codex, powered by Cosmic Charades. We are thrilled to have you all, the space fans, astro enthusiasts, with us as we embark on a journey through the wonders of the universe, exploring the latest discoveries and advancements in astrophysics and cosmology. So, Cosmic Shred is a multifaceted platform promoting science through courses like R programming, numerical mastery with Python, approaching towards computational thinking with both R and Python, as well as science blogging platform, magazine featuring articles, sci-fi stories, and creative works, and the very special segment that is Cosmic Verses initiative for art. Uh, Literature and photography. Its podcast, Cosmic Codex, explore interdisciplinary cosmic mysteries with experts. So recently, we rocked the cosmos with our first magazine launch at the Kolkata Book Fair 2024. We are now back with something even more stellar. So get ready for our second issue, the Sharadiya Shankha, uh, which will be dropping just in the time for Durga Puja in the month of October. So stay tuned and stay updated for another cosmic ride with us. So today we are privileged to have a distinguished speaker with us. Please join me in welcoming Mr. Subhendra Das with his session titled "For the Search of a New Home" and the episode "Cosmic Voyages." So Subhendra has done his BSc in physics from Vivekananda College, Thakurpukur, and done his masters in physics from Rajabajar Science College of Calcutta University. Currently, he is pursuing his PhD at the Physical Research Laboratory, Ahmedabad, Gujarat. His area of interest is broadly based on exoplanet research. So, if you are looking for a new home with the fam, so stick around till the end of this session. You will get a new place shortly in this cosmic horizon. So, over to you, Shubhendra. Thank you. No, I think you are not audible.
Am I audible now?
Yes, yes, you are audible now.
Okay, let me present my
Yeah, I am
slides.
stop sharing. Yeah, you can present now.
Okay, just give it a minute.
Okay.
Okay, Google Slides, share. Can you see the screen?
Yes, yes, it's visible. Yeah.
Okay, and can you see my cursor?
Yep.
Okay, fine. So let's start. And thank you, Shamrit, for the invitation and the introduction. Now, as the title and the image suggests, today we are going to talk about exoplanets. Now, I have tried to keep this talk very general, and I will try my best to finish this within 1 hour. There is no as such prerequisite for this session. School level physics, I think, will be more than enough. Now, I have structured today's talk broadly into three parts. In the first part, I will give a brief introduction about how our interest grew for exoplanets over the time and the classification of exoplanets. The second part involves how we can search for exoplanets. And in the last part, I will show you how you can play with readily available archival data and maybe you can try to find a exoplanet on your own. Now, there is now here is a table of content that I have just said. Okay, so here is a cartoon picture of our solar system, and we know about it from our school days. Most of the planets we are seeing here were known to the mankind for a long time, and here this is our Earth sitting in a very comfortable zone in our solar system where we can get water in liquid form. Also, this is the only known planet with life. Now, if you look to our solar system with a curious mind, you can see some patterns. Okay. Now, from this figure, also you can see the rocky planets like Mercury, Venus, Earth, Mars are in a closer orbits or very closer to the Sun, whereas the gas giants are in a far away orbits or in a larger orbits like Jupiter, Saturn, and there are icy ice bodies like Neptune and Uranus. Now there are other patterns too. See, here is a face-on view of the orbits of our solar system, of orbits of the planets of our solar system. Here you can see that most of the planets have a fairly circular orbits. Okay, those orbits are seem not to be like ellipse, but with the Mercury having the highest eccentricity with around 0.2. And before its demotion from the planet status, it was Pluto with eccentricity of approximately 0.3. Now, this is the view of the inner planets, where you can see the planetary orbits are circular. Okay. Now, if you see our solar system on a edge-on view, then you can see that orbits of the planets are in a plane, in a single plane. They are not like it's in the orbit's inclination is not that much. There are orbit inclination, but it is not very high. And we have here is the like Jupiter's orbit, which is the least inclined, and the Mercury object, which is the most inclined, with around 7 degree of inclination. Okay, so let's list those facts again, right? The rocky planets are closer to the star, and the gas giants are far away from the star. Orbits are circular. All orbits are in a plane. In our solar system, the closest planet is Mercury with a semi-major axis or the distance as zero point 0.4 astronomical unit, which is around 60 million kilometer, and the farthest is the Neptune with a 30 astronomical unit. Okay. Now, eventually, with the detection of newer planets, those facts faced many challenges and make us rethink about the way we thought about the formation of planets. Now, here I have listed one or two examples of exoplanet extremes. More you can find on Wikipedia. Okay. Sorry, another one thing that the Jupiter is the largest exoplanet that we know. Okay. So here, the first thing is that what I have said that our orbit of the planetary orbits in our solar system is fairly circular. But we have also found a planet HD 20782b with a eccentricity of 0.96, very close to 1, which means it's like in a very ecliptic manner and very close to a parabola, but and it's very interesting to think that how it can manage its orbital dynamics and stability. And here is a planet with a radius of approximately 3 times of Jupiter. Now, with these facts, the we can say that there are many more other examples of exoplanet extremes. Okay, and with those examples, our knowledge about the upper limit of planet size, mass, the lower limit of size of orbits, the upper limit of eccentricity got challenged. Now there are many more these type of exoplanet extremes examples from the year of 1992 to the current time, a diverse range of exoplanets have been discovered. Here are a few milestones of this field, which include the detection of first exoplanet around a pulsar in 1992 to the first exoplanet around a sun-like star by Professor Michel Mayor and his student Delia Coelhos, which eventually led them to the winning of Nobel Prize in 2019. Then discovery of Earth-like planet of Kepler 186f in the habitable zone, and to the date we have discovered more than 5,500 exoplanets. Okay, here are some here is the historic timeline of exoplanet exploration. I am not going to stop and explain every photographs. You just can, if you want to know more about this, you can just visit the website mentioned in the image credit. Okay. Now, with the cutting edge technologies and different detection techniques, a large number of exoplanets have been detected, and the numbers are increased to more than 5,500. Now, here I am showing you a GIF of the history of exoplanet detection, where the x-axis is the period and the y-axis is the mass. Here you can see that first of all, the total number of exoplanets is 5,747, and this is till the date of 24th August. Here in this plot, you can see a history of exoplanet detection using different methods. Here we will see some dots, some green dots, red dots, blue dots, yellow dots. Those green dots are the exoplanets detected by using radial velocity method. The red dots are for the exoplanets detected using transit method. The light blues are for the imaging, and the yellows for the microlensing. I will discuss these methods later on this talk. But here you can see that before 1995 there are only solar system planets, and now in 1995 there is a green dot. That means the detection of the first exoplanet, which was 51 Pegasi b. At 2003, the red dots from the 2003, the red dots getting increased, right, because of the Spitzer mission. And from 2009 there was Kepler. So if I say from 1995, initially the radial velocity method dominates the field, but after the space-based missions, Spitzer Kepler test, the transit method started to dominate the field. Now, till the date, with radial velocity method, we have detected around 1100 planets. With transit, the number is around 4,300 approximately. Now, if you look at the plot very closely, you can see that with transit, we have discovered planet with high mass, but a smaller orbital period. Okay, and with the radial velocity, we have detected planets with higher mass. Now, why are these things going to these things are happening? Is this any bias, or is this the fact that there are more exoplanets in the lower orbital period? That thing we will going to discuss when I will discuss these methods in brief. Okay, so before going into the detailed discussion of exoplanet detection method, here I would like to show you a very brief and brief classification of exoplanets. Mainly the exoplanets are classified into four categories: gas giants, Neptunians, terrestrials, and super Earths. Now, why I am showing you these three? Because these three classifications are based on they're based on the planets that we are having in our solar system. And there is another type which is called super Earth. We don't have it in our solar system, but we have found this kind of planets around the stars. Now the thing is that here I have shown you some boundary conditions for those gas giants, Neptunian, terrestrial, based on the radius and the mass. I just want to clarify that these boundaries are not very strict boundaries, and personally I don't like the classification. but yeah, it's been using people is using this classification for a long, very very long time. So we are going with the flow. So our so when you look at the sky, you can see stars and our solar system planets, right? Now, but you can't actually see the exoplanets. Now, that is why most of the exoplanet detection techniques are indirect. Now, they search for evidences that can be there if there is an exoplanet. If you can see the exoplanets and their orbits around their host stars, then your perception on those orbits can be divided into three parts, because our detection methods depend on how we are perceiving those orbits. Now, it's really a point of view kind of thing. Okay. Now, if we assume that our computer or phone screen is the plane of the sky and we are looking at it, then the planet orbiting in that plane, that we'll call a orbit, or a orbit within a face-on manner, or a face-on orbit. Now, in this case, no transit will be visible. Now, in this context of exoplanet, transit is the phenomenon when a planet just pass by in front of a star, where the plane of the orbit aligns with the viewing direction to the star. Therefore, we can see a blocking of the star's light. Now, in this scenario, when we are looking at this orbit, we will not be able to see any light blocking. But if the orbital plane becomes perpendicular to the plane of sky or your computer, then you can see the dimming of the star due to the transition of the planets. Now, I will show the examples. But now, here for this kind of orbits that you are currently seeing on your computer screen, direct imaging and astrometry are the most viable choice for your detection. I will discuss these methods later. Okay. Now, if the orbit starts becoming more inclined, then the other methods like radial velocity and transits becomes feasible. Now, if the orbit is in exactly perpendicular to the sky, to the plane of the sky, then the radial velocity and transit methods become the top choice. Now, let's start with the direct imaging. As the name suggests, it relies on taking direct picture of the star and try to see if there is any planets or not. Now, seem very straightforward, right? But there are some catches. Now, it's not like the picture taking we are familiar with. Okay, like it's kind of a picture taking of a firefly sitting on a halogen lamp. There is a huge contrast ratio. Well, in the case of firefly, you can just turn off the lamp, but you can't turn off the star, right? So now, if you assume that the star is a black body and it emits the light as the black body, so from the temperature, you can say that for a sun-like star, the star will be more bright in the visible band. Okay, so it will be good if you, or if you try to take the picture of the star where the star is lesser bright, so in the higher wavelength region, okay, or in the longer wavelength region. See, in the left hand side panel, you can see a plot of the flux of the star. Here I have taken the example of sun and the planets we have in our solar system. Here you can see in the visible region of around 500 550 nanometer, the difference between the star's brightness and the planet's brightness, it's around 10 billion. If you shift towards the longer wavelength of 10 micron, then the contrast ratio become around 10 million, which is still pretty high, but in the comparison with the visible range, it's lesser. Okay, so I will suggest that if you want to do the direct imaging, then go for a longer wavelength. The same example you can see in the right hand panel here. In this part, you can see that it's a visible image, visible band image of a star, and you cannot see a planet here, right? But if you go for a longer wavelength band and take the image, you can see the planet here. Okay, the star is not so bright, so the contrast ratio is lesser. But the getting a sharp image is tough. Why I'm saying that? See, when you see a star in the sky, you see it as a point object, which means it is as a Dirac delta function. Now, when that starlight enters the Earth's atmosphere, the photons get diffracted due to the atmosphere. And photons, then those diffracted photons will be collected using your telescope, and due to the diffraction of the lenses or the optics of the telescope you are using, the photon will get diffracted more. So your Dirac delta function will get broader and broader. So the broadening of the star, of the pointy nature of the star due to the Earth's atmosphere, is called the seeing. And when that thing again broadened by the telescope and the telescope, all the telescope systems, it is called the instrumental profile. Now, what is the problem with that? See, if there are two very close objects in the sky, which are pointy objects and you can distinguish them, if they get broadened enough, they will start merging because their position will not change. At those positions, they just get broadened or bigger. So those two objects in the sky diffracted here due to the atmosphere and become hard to separate. And when you capture it by your telescope, it's become more hard to separate and like harder to separate. To reduce the effect of diffraction due to the atmospheric turbulence, people use adaptive optics. It's a whole different technique of observation, or they go for space-based observations. Now, the problem with the direct imaging is that either you have to go for adaptive optics or you have to go for space-based observation, and both are tremendously expensive. There is another method which is called coronagraphy. In the coronagraphy, what we do, we just block the central portion of the star, or the central portion, which is the star, and we can try to see if we can see the planets. This method is also be done in a longer wavelength, and as well as for space-based observatories. Okay, this image is taken by JWST, where you can see the presence of 3 planets around this star HR 8799. Okay. Now, there is another method called astrometry. Now, for those face-on orbits, there is another thing is happening. See, from the classical mechanics and two-body system, we know that if there is two body bounded by a attractive force, in this case, which is gravity, then both those two bodies will rotate around their common center of mass. In the case of a planet and star system, the point of center of mass is way closer to the star because the star is very massive. So therefore, you can see a very large orbit for the planet and a very smaller orbit for the star. As you can see, that the planet is rotating around the star, and also the star is kind of wobbling. Okay. Now, the astrometry based on the precise measurement of the star's position. If you somehow pinpoint the position of the star, and if you observe for a very long time, you can see that the star positions will get periodically changed. And from that change, you can infer that these changes may be due to the effect of a companion planet. Okay. Now, for the edge on or inclined orbits, there are two very successful methods, which are transit and radial velocity method. See, the transit method is kind of an imaging method, and the radial velocity is a spectroscopic method. What happens in a transit method? When a planet just pass by in front of the star, it blocks some amount of light. Okay. Now, if this happens periodically again and again, again and again, then you can infer that there is some periodic light blocking, and from the ratio of their sizes, you can say, like, from that dip in the brightness, you can infer the ratio of the planets and stars radiuses, and from that you can get an idea that okay, there can be a planet, and using some analysis you can finally find the presence of the exoplanet. The main perks of using transit method, that it gives you radius. Okay. Now there are several other factors which also can be obtained from the transit methods. Now see, from the spectral type of the star, you can get the mass of the star. Okay. And from periodic appearance of the transit light curve, you can get the period of the planet. From the period and mass of the star, you can get the semi-major axis of the orbit using the Kepler's third law. From the semi-major axis and the transit duration of the system and the period, you can get the idea of a radius of the star and as well as the inclination angle. See, here you can see that it's a clear edge on orbit, and in this case it's kind of inclined. Okay. And from that radius of the star and the transit depth, you can get an idea about the radius of the planet, which is a very important characterization parameter for a planetary system or a planet, and which is the main USP of transit method. See, there is a very good disadvantage for the transit method, which due to which we cannot go for ground-based transit surveys. Okay. See, the main disadvantage with the transit methods, that it's a very low probable method. Okay. Now you can see that if there is a star and here is a planet, the transit can only be visible if you are inside that cone of transit visibility. Okay. Now, if the planet is here, see, the orbit is kind of like this along my cursor, then you cannot see a transit if you are looking at this direction to the right side of your screen. So the probability of transit is approximately the ratio of the star's radius and the semi-major axis. And for the Earth, it is around 5 by 1000. So transit method, is in the favor of very short period planets. Okay, so if the A is very small, then it's more probable that you can see a transit. That is why when I show you the plot of mass and the period, the transit methods will lie in the low period orbits. Okay, so the main disadvantage with the transit method is the low probability of discovery. Okay, and the problem is that with the low probability of discovery, you have to like do this surveys for a large number of stars, and with the ground based observatory or ground based systems, it is not very feasible. That is why we go for a wide sky surveys like Kepler and TESS. The main difference between the two missions, that Kepler was looking at a particular direction, like which is around like 0.25% of the whole sky, and the tests were looking for the all sky. So with this you look for a large number of stars and you get a large number of transiting planets. Now there are several disadvantages of the transit methods too. Despite having the low probability of discovery, there can be a brown dwarf or a low mass star orbiting your target star. In this case, you can also get the deep in the total light of the star, the transit shapes. Also, if there is a grazing stellar binaries, grazing means the smaller star is going from the very lower part of the of your target star. Okay, for this kind of thing also you will get a very small deep of the transit light curves. If see, if this small star goes just front of the your front of your target star, the dip will be very large, but in this case the dip will be very small. So you can get confused that whether it's a planet or it's a star. Now there is another method which is the radial velocity method. Now this method use Doppler effect. We all know Doppler effect, that if a body like comes toward us, the wavelength get squeezed and becomes blue shifted. If the body goes away from us, the wavelength gets stretched and get red shifted. Now, as the target star is moving due to the presence of the planets, and this movement is along the observer, then we will also can see this kind of stretching, in a kind of periodic stretching and squeezing in the star spectra. Here you can see that if here is the observer, the star is coming towards you and going back. That is why from a time series of observation of the speed or the Doppler shift of the spectral lines, you will get this kind of sign or this kind of periodic functions. Here you can see that if these dotted lines are the true position of the spectral lines, due to the presence of this planet, the star's spectra gets red shifted and blue shifted, red shifted and blue shifted periodically. Here is the actual radial velocity plot of that 51 Pegasi b, which was the first ever detected exoplanet and detected by these two guys. He's Michel Mayer and his Didier Queloz. They discovered this exoplanet, and you can see a nice sine curve, okay? Just like this. From this method, you can measure the mass of the exoplanet, which is the main USP of this method. Now, there are mainly two features of a radial velocity curve. A radial velocity semi-amplitude, which is simply the half amplitude of the sine curve, and the radial velocity error, or the sigma RV, which is the error of each data point. Okay. Now, this radial velocity semi-amplitude gives you the idea of what can be the mass of that exoplanet, and with a lower value of radial velocity error or the sigma RV, you can detect a lower value of RV semi-amplitude with a lesser number of observations. Okay. So the main three things that you can get from a radial velocity method is the period, eccentricity, and the mass of the planet. And where the mass of the planet is the main USP of radial velocity method. But there are also some limitations of the radial velocity method, which is C. If we consider Earth-like planet around a Sun-like star, then the star will also wobble around the center of mass. But that the wobbling would be like the velocity of a turtle. which is around a few tenths of centimeter per second. For our Earth, the sun wobbles is around 10 centimeter per second. And you have to detect this kind of small variation in star's velocity, which is really, really very hard. Now, what we do and why it is very hard. See, in the radial velocity method, what we do, we measure the shift in the spectral line. Okay, if this is the true position of the spectral line, we observe that okay, here is the measured position of that particular spectral line, and here is the delta lambda. So this is the shift. But this is not the actual case. Now, when we target few meter per second of radial velocity, the on-sky effects as well as the instrumental effects show dominance. See, now here you can see that from the true position to the measured position, there can be a shift due to the effect of the star itself, due to variation in your instrument that you are using to measure that shift, and the Doppler effect, and you want to measure this value. So if this instrumental effect and star value and the effect from the star become a dominant feature, then it will be very hard for you to detect such small shifts. Okay, so we have to use a very stable spectrograph, and we have to look for the star. If it's a very active star or very inactive star, then you can get some idea. Okay, this is the RV shift, the radial velocity shift in wavelength, and from that you can get the velocity as well as the mass. um, here is a method that how you actually take the spectra of the star to do your radial velocity method. Okay, see, there is, if there is a star, you are taking the picture of the star using your telescope, and you pass the light through a spectrograph. And it's a very generalized schematic of a spectrograph. High resolution spectrographs generally contain a collimator to parallel those light beams. A shell grating, it's a very special type of grating for having large resolution, where we can get a large number of lines. A cross disperser to get this kind of spectra. If see, the Eshel spectra are overlapped, you can see the Eshel spectra in a single line, overlapped each order on one order on another. To make them separate, you have to use a cross disperser and the focuser to just focus the light on a CCD detector. For each order, you can see this kind of spectra. Here you can see a kind of a continuum, like it's increasing then decreasing. This is called a Blaze function. It's a property of that Eshel grating. So from that you can reduce the spectra and from in your pipeline and get a nice spectral feature. And from that you can have your exoplanet detection things. See, there is, as I say, that there can be instrumental effects as well. Now, what we are trying to measure here, the shift in those spectral lines. Okay. Now, those spectral line shifts coming from the star can be due to the instrument as well, due to the telescope movement, due to the movement of this optics as well. For this, what we do, we use a wavelength calibrator, which is a simultaneous wavelength calibration technique, where you just put a off-sky source through the same path and see that if there is any shift in that, in the spectral lines of those, of that wavelength calibrator, and then we can subtract that effect from the shift we are getting for the starlight. Okay? So the starlight also following this path, and the calibrator light is also following this path. So if there is any instrumental shifts that can be get picked from that shift of that wavelength calibrator's lines and can be subtracted. So for the radial velocity method, a high resolution spectrograph is needed, which can give you a large number of lines. a big telescope is needed, which can give you a large collection of photons, a good SNR, and a stable spectrograph is needed, or a good wavelength calibrator is needed. See, the whole point of the radial velocity method and the transit method is to having the mass and the radius of the exoplanets, which are the main characterization part of a planet that you are seeing. From that mass and the radius, you can get idea that okay, there can be this planet at this distance from the star, and from this you can have idea about your planet formation techniques. Also, from the temperature of that planet or the position of the planet away from the star, you can get an idea about whether there are liquid water or not. Okay, so this is the first part of the talk. So if you have any questions, you can ask. Then I will go for the hands-on part with the transit data. Okay. Ah, okay. 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 Yeah. 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 Okay. Just a second. Let me go to chat. Okay. Okay.
Yeah, so the first question I put it in the chat. Can you see now?
Okay. How do you know there is or are exoplanet and exoplanets in our solar system? Okay. First of all, the term exoplanet means it's extrasolar planets. That it doesn't include planets in our solar system. Um, what is we put our solar system in intergalactic space, then what will gonna change in it? Okay, what is we put our solar system? Okay, we are in intergalactic space, so I don't think there will be a much change. I
Hmm.
hope.
Okay. Okay, I
Okay.
hope it answers the questions we have asked. So the next one is this one.
Okay. Um, After MSc Physics, what are the best universities in India and foreign for PhD in observational astronomy? Okay. In India, there is Physical Research Laboratory, of course. Also, in Aries, I think they are doing observational astronomy. And if you are talking about foreign, then I will suggest Observatory of Geneva. They are doing pretty good stuff because the first exoplanet detected was from there. Okay, so Observatory of Geneva is pretty good.
Okay, so there is another one.
Okay,
It is kind of comments, not like a question, but yeah.
okay. Application of Q dots. I don't know what is the Q dot.
Yes,
Uh,
so whoever asked this question, can you please come up and explain what is Q dots? Uh, I don't know who has asked this question. Let me check. Asha, one. Yes, Shibham, you have raised your hand. Yeah, unmute yourself and say, or if you want to write down in chat, you can. Shibham, are you there? Shibham, you have raised your hand, I saw. Anyone from this meeting? Anyone from this? Any question? Okay, so Obhirup has a question.
Okay. Okay. What are the biggest unsolved question in this field? Fine. Okay. First of all, we don't know whether there are lives lives in extragalactic planets. Second of all, the main thing is that we don't know ki, how these planets are formed. Okay, see, in our system, we see that Jupiter like gas giants are in outer orbits. But in the case of the exoplanets, we have found that there are very close in Jupiters also. One such exoplanet was discovered in India, uh, was by one of my seniors. It is I think TOI 1789. It was a very hot Jupiter and a very close in orbits of around 5-6 days of orbital period. Okay, so this is one of the biggest unsolved question, and yeah, I think these are the biggest questions that are really unsolved in this field.
Yeah, and also I just to add your point that the kind of life form that is present or might present in that particular planet is still unknown to us, right?
Yeah, actually, the thing is that see, when you look at the exoplanet or when you try to find the exoplanet, what you try to find its mere presence.
Hmm.
Now, the second thing is come that whether there is life or not. Now, how you can check that whether there is life or not? You can check for the atmosphere, right? So
Yes.
in our atmosphere, you can have nitrogen, oxygen, and this kind of thing. So there is a technique called transmission spectroscopy, where you can have an idea about what are the materials or the things are going on in the atmosphere.
Hmm.
But for that, you have to use a very large telescope because the signals you will get from a transmission spectroscopy is very low. It's very low. So I think there is a one 30-meter telescope is currently building up in. So with this, I think we can do the transmission spectroscopy.
Hmm.
But with smaller telescope, it's impossible.
Yes. So another one has raised his hand, Hari Krishnan. So yeah, can you go ahead if you have any question?
Sir, what about the wow signal, sir? Is the signal is originated originally from the any extraterrestrial civilizations or from like a supernova explosion? What is the exact definition, sir? What about the current understanding about the
Okay.
wow signal?
Okay. Biosignatures. Okay. When you talk about biosignatures, there are two things. First of all, there have to be liquid water, right? First of all, biosignatures, when you talk about, there are some spectral lines of nitrogen, mainly nitrogen.
Hmm.
We try to find if there is nitrogen in the atmosphere. With the nitrogen, you can say that, okay, fine, there can be a biosignature there. So
Okay.
having, so there are something like CN lines. So there are some molecular lines you find in the spectra coming from the planet's atmosphere. Using that, you can say that okay, there can be biosignatures. Also, you have to check that whether this planet is in the habitable zone or not. See, I
Okay.
think if
Okay.
you're trying to find that if there is any life or not, see, you can say you can have nitrogen in the atmosphere, but if the planet's orbiting the sun in 2 days, you can guess the temperature of the planet is around 2000 of 2000 Kelvin, and no life can sustain in that high temperature. So you have to check for the temperature of that planet also.
Okay.
Okay, there are few more questions. Can you
Yeah.
talk a little bit about what you work on this field? Okay. Currently, actually, I work on the exoplanet instrumentation. So, as I have shown you that there can be wavelength calibrator needed and this kind of thing, and that sigma RV, that the radial velocity error. My main research area is to reduce that radial velocity error from the instrumental point of view. Okay. Another question is that what extra information can we know about exoplanets? For example, we can know about the temperature, inhabitability, etc. But can we know about its atmosphere and maybe age or history of planets? See, we can know about its atmosphere. There are some theoretical modelings, but if you want to observe this thing, you have to go for the transmission spectroscopy. And another thing is that from the you actually can observe, you can get a guess of the age of the system from that age of the planet, age of the star actually. So you can look like the exact history; those things kind of can be answered using the models. Okay, not and those models are in a in a field of growing research. These are not they are not very perfect. They cannot perfectly answer your question. They can give you that yeah, this can be possible. This kind of answer. Could there be exoplanets where life exists, but they are so radically different from Earth's that we would fall to recognize it as life at all? Okay. Um, okay, we don't know that. Okay, first of all, what do you mean by life? Okay, so and there can be exoplanets where life exists, but first of all, detecting them is really hard. Okay, what are the conditions for habitability? Okay, for habitability, first of all, you have to look for liquid water. That means your planet's temperature have to be around 300, 400, 300 or 350, 330 Kelvin. For the case of a sun-like star and a Earth-like planet, or any kind of planet, your planet have to be situated at around 1 astronomical unit or 150 million kilometer from the star. Um, if some different life form prefer a different habitability conditions than Earth, we could misidentify them as inhabitable. Okay, actually, when we define the habitability conditions, we consider ourselves and like the life we can see on Earth as the exact life forms. So we made those conditions based on the lives that are on Earth. There can be many things. Okay, the possibilities are infinite. Uh, is it possible that some exoplanet possess environment that enable natural creation of technological artifacts, giving the illusion of an artificial civilization? Okay, it can be. It can. Like I can't comment on this thing because what we do is mainly based on what we can see. If we cannot see it's there, so we'll say it's not there. Okay. Can we make universal language to connect with extraterrestrial civilization? First of all, we haven't detected that whether there are extraterrestrial civilization or not. If there are, then we can make some kind of universal language to connect with them. Are there exoplanets orbiting rogue black holes where light is burst but life exists using other energy sources like geothermal or magnetic activity? Okay, actually, um, we haven't detected any exoplanets around black holes because most of the techniques are based on the lights coming from the most of the techniques mainly coming from the lights of the star. Also, without solar energy, as well as planetary bodies achieve those temperature due to radioactive decay if present in considerable amount. So there can be a problem. Okay, is there any other questions? Okay. What if there are exoplanets hidden in the dark matter of the universe, invisible to our current method of detection, but teeming with life? Okay. Um, I don't know if there can be exoplanets in the dark matter of the universe, but all our methods are fairly based on what we can see. So I don't have many idea about how those dark matter affect the planetary conditions. So I think I should not comment on this question.
Yeah, so actually we have to detect dark matter first, then
Yeah,
we can answer this question, right?
yeah, yeah. But there are like different kind of dark matters also, like baryonic, non-baryonics.
Yeah.
So
Mm-hmm.
we have to first detect the black matter, dark matter. Then we can
Mm-hmm.
go for exoplanets in the dark matter scenario.
Mm-hmm. Yes.
How do you know about the atmosphere? Yeah, mainly spectroscopic analysis. Yeah, yeah. Spectroscopic analysis is a very good way to detect about the atmosphere. See, when you take the spectra, na, for the stars there are atomic lines, and for the planets there are molecular lines. Now, in that spectra, if you detect some molecular lines or molecular bands, I mean not lines, mainly bands, then you can say that okay, these bands only can come from the atmosphere of the planet. So from that you can guess, or you can get an idea that there can be atmosphere around the planet if you are talking about observationally seeing that. Okay,
Mm.
is there any other questions? Okay, by the way, are the observation data open? uh, if we have time, I can show you some observation data. Just wait a minute, huh? Wait a minute, let me join.
Okay, okay,
Just
sure, sure.
let me show you. um, I'm going to stop sharing from this screen and started from another screen. Share. Okay. See, here you can use the transit light curves data. Okay. Here, there is a module in Python called light curve. Using that, you can do some codings. Okay. So here we are using a Kepler data, which is uh, which is a like sky-based observation, Kepler. Kepler 8b, it's a very confirmed planet. And for Keplers, there are many quarters of data. Now, if you use stage, that will be sector. Now, you can import the light curve and download the data. I have downloaded the data of the quarter 16. You can go for any quarter you want. Okay. So in those data, you will see the time, flux, the error in the flux, and some other quantities. If you plot the light curve data, you can see this kind of plot. There is periodic dips, right? You have to flatten the data first because the counts you are getting here that can be biased by your instrument that you are using to see that target. So you have to like flatten and normalize the data. With this, you can get this kind of nice lines. Now, if you want to find the periodicity of the planet, you can use a tool called the periodogram, and you can use the box least square method, which with which you can find the period also. Here we have detected the period of around 3.522 days, which is very close to the actual period of the planets, which is around 3.5225 days, differ by only 1 second. Now you can fold the data and remove the NAND, so you can get a single light curve, and you can feed some models to this light curve data to get idea of the radius of the planet as well. Here I have actually used a model. Here is the model based on a paper of Mandel and Agol. There I have detected that this planet have a semi-major axis of 10.899 solar radius, and the radius of the planet is around 1.411 Jupiter radius. So with this, you can just play with online available data. Does this spectra affected by cosmic radiation? If yes, so how do we handle it? Okay, for the cosmic radiations, when there are cosmic radiation data, they actually like removed. They actually find for the your cosmic radiations data points on your like CCD detector or your image, like they actually find for some random points. Okay, and from those random points they take that, okay, fine, this point is coming due to the cosmic radiation or your cosmic rays, and they remove those random points or random lines. So this is how they get rid of those cosmic ray points. But when you actually download those data, you cannot see those cosmic ray points, because actually these are not raw data actually. These are kind of processed data using a pipeline. Can you share any sources for openly available data? Uh, okay. If you want spectral data, there is exopop. I will share it with Samrit, and he can share it with in the group. Okay,
Yes,
I
yes,
will share.
sure. Yeah, sure.
I will share this. Okay. Is there any other questions? I hope not. Okay, okay. So, thank you. Okay, fine. Thank you, everyone.
Yeah, so I think there is no question left. So, okay, we can wrap up this session. Thank
Okay,
you
thank
once
you.
again, Nath Dash, for your wonderful sessions. We have discussed about exoplanets and all other matters. And yeah, it was very nice session to me as well. So thank you once again.
Thank you. Thank you,
Thank
everyone.
you
So
everyone for yeah.
I will share with you the link for the for link that where you can download the data. Okay, you can.
Okay, okay, okay. Thank you
Okay,
very much.
okay, thank you.
Yeah.
I have
Okay.
already
Yeah,
joined the group.
Shamli.
You may share there.
Okay, okay, I will share that. Okay,
Okay.
Okay.
Great.
so I'm leaving. Okay, okay. Thank you very much. Good night.
Yeah,
Yeah.
Shamrit, I have an. I want to say something.
Yes. Yeah.
Yeah, so there is a announcement. So the announcements regarding the tomorrow's problem solving session. Okay, so Shuffle Das Bishwas from ISI Bangalore. He pursued his BMAT from ISI Bangalore and currently pursuing his masters from uh, Ramakrishna Mission Belur Mott. So RKM Vedi. So he will be taking his free problem solving session tomorrow, and we'll be starting our session tomorrow 8 p.m. And the free participation certificate will be available. Okay. So I'll request please join the tomorrow's session those who are interested. Okay. Thank you.
Yeah.